Hi everyone, welcome to another tutorial on LSAT. In today's video, we'll look at an easy introduction to the chi-square goodness of fit test. We'll also use it to determine if a data set is normal. Along the way, we'll take a brief look at the concept of binning and why is it so important. We'll also try and get an intuitive sense of what are chi-square distributions. So let's begin. Chi-square distributions are a common entity that you often see in the field of statistics, but you also get to see applications of chi-square distributions in biostatistics and social sciences. So what is a chi-square distribution? So a chi-square distribution is nothing but the square of a standard normal distribution. Quick recap, what's a standard normal distribution? Any normal distribution which, when reduced in a manner such that the mean becomes 0, and the standard deviation of that data set becomes 1, reduces it to a standard normal distribution. A quick bit of history around the chi-square distribution. These were first discovered around 1870 or 1880 by Robert Helmert. And then subsequently, there was a lot of work that was done by Carl Pearson, the father of modern mathematical statistics, around 1900s. In fact, he also came up with the chi-square statistic, which is one of the key things that is utilized in running any chi-square tests. So what are chi-square tests generally used for? So they have quite a few applications, but there are some main or primary applications of chi-square distributions. These include looking at a theoretical distribution and comparing that with actual observations. In fact, when we try and run a normality test or check if a data set is normal, we are in effect checking if the given distribution matches the theoretical normal distribution. The other common application that you will see of chi-square distributions is going to be in checking if two data sets are similar or basically they are associated or not. Bear in mind that this is only possible for categorical variables if you're running chi-square distributions. And the third application, and not very common one that you'll see in practice, but it is used, is checking the variance of a single population. Now, having said that, what you see on the screen right now is a normal standard distribution. And when you create a chi-square distribution out of this, which is nothing but the square of a standard normal distribution, you end up with different graphs. An important thing to remember is that chi-square distributions depend on the degree of freedom. So what are degrees of freedom? So degrees of freedom represent the number of different normal distributions that you're actually using. So if you're using only a single standard normal distribution to generate or create a chi-square distribution, you would be using the degrees of freedom equal to 1. On the other hand, if you add up two different normal standard distributions, then your degrees of freedom is 2. If you add 3 normal standard distributions, your degrees of freedom is 3, and so on and so forth. So what is the net effect of this? To understand the net effect of this, remember that if you were to do a square of the z curve that you see on the screen, how would the corresponding curve look like? Well, let's take a look at it, and we'll just try and draw the corresponding curve here. Yeah, this will work. So if we were to draw a corresponding curve, what you'll see is that the corresponding curve looks very similar to what we are making on the screen right now. So this will be a curve which will come very close to the y-axis, and then this curve will again curve right at the bottom and remain very close to the x-axis as well. So this is the shape of the degrees of freedom 1 chi-square distribution. Why does this shape result? So the reason you have this shape is, remember that you're squaring up values. So for any values that are less than 1, remember that when you square a value which is in between 0 and 1, what transpires is that the value becomes even smaller. So as a result, you'll see a lot of congregation of values around the y-axis, and then the curve flattens out at the bottom and then runs along like an asymptote along the x-axis. So that's what results in this shape that you're seeing right now. What happens if we were to create a chi-square distribution with degrees of freedom 2? Well, in case you try and create a chi-square distribution, let's say with degrees of freedom 2, the resulting curve that you'll see from there will be a bit like this. So you'll see that this is a shallower curve as compared to the one that we just looked at. And this would be the resulting shape of the chi-square distribution. All right, let's also take a look at what happens when you increase this further. So let's say you were creating a chi-square distribution with degrees of freedom 3. In that case, what you'd notice is something very interesting happens. The shape of the curve radically alters in that case. And what you'll end up with is a curve similar to the one that you're looking at right now. All right. And then on subsequent chi-square distributions of a higher degree, like chi-square distribution with degrees of freedom 4 and above, what you'll see is, you'll see that gradually the curve starts to represent a bell curve or a normal curve more and more. Eventually, if you were to keep increasing the degrees of freedom of the chi-square distribution, this closely comes to approximate a normal distribution. All right. So this is a brief introduction to what is a chi-square distribution. Let's delve into this a bit further. So if you look at what you have on the left-hand side is an image or a small GIF video which shows you how the chi-square distributions will kind of look like. So what you see right now is the moving image, which gives you an idea as to the different pictures around this. Okay, so all right, let's go ahead and stop this. In fact, yeah. So what you see on the screen right now is very similar to the degrees of freedom 1 chi-square distribution that we just looked at right here. That's the red colored line. Let's play this further. This becomes your degrees of freedom 2 chi-square distribution. This will then, if you were to play this further, let's take a look. That's your degrees of freedom 3 chi-square distribution. Gradually, you'll see this tends to take on more and more of a Gaussian distribution or a bell-shaped curve, just like a normal distribution does. On the right side, you have the mathematical equivalent of it. This is how, so basically, the square of the normal standard distribution will be your chi-square distribution, degrees of freedom 1. If you were to add up two separate normal standard distribution, you'll end up with a chi-square distribution, degrees of freedom 2, and so on and so forth. All right. So much for the mathematical equivalence of this. Now let's quickly move on to the problem statement. So what we're trying to solve here is we're trying to check if this given data set that you have here, if this is a normal data set or not. We already know that there exists many ways of checking if a data set is normal. What you'll come across most commonly are going to be the Kolmogorov-Smirnov test. Another common test that you see often in statistical packages is the Anderson-Darling test. But those are not the only test. We know the Harke-Bera test from previous video, and I'll leave a link to that. In addition, what you can also use is a chi-square goodness of fit test. So what exactly is a chi-square goodness of fit test and how is it applicable? So let's try and understand that. Consider these following three distributions that you have on the screen right now. Assuming that all these three distributions have the same mean and the same standard deviation. If we were to say that the first distribution that's in blue color is a known normal distribution, we know that it's a normal distribution. Now look at the two other distributions that we have in orange as well as in green on the far right. If you just were to look at it visually, which one of these two, the green one or the orange one, which one of these two do you think is a normal distribution? Well, if you observe that, you'll see that the green colored distribution right here comes very close to being similar in shape to the known normal distribution. On the other hand, you can clearly see that the green colored distribution is skewed in a strange way, and this does not look like a normal distribution anyway. So at the very outset, just by pure observation, you can say that this is unlikely to be normal. On the other hand, this is more likely to be a normal distribution. Okay. So how did we come to this conclusion? The way we came to that conclusion is by comparing each of the class intervals, which is, if we look at the first class interval right there and look at the first class interval right there, they seem to be pretty similar. And then we move to the next class interval, and that one also looks pretty similar. And then the next one is similar, and so on. So they're similar in height, right? And as you know that on a histogram, the height of that particular class interval tells you the frequency of that class interval, or the number of occurrences in that class interval. By the way, class intervals are also known as bins, and that will be important for us later. So I think the understanding that we're trying to drive on this one is, remember that if you have a distribution which has a similar number of occurrences, or similar frequency for each of the class intervals when compared to a known standard distribution, then you can safely say that the given distribution is also a normal distribution. So that is the simple concept behind all of this. So now, how is this going to be used in determining if a data set is normal? So the way this will be used is, for each class interval that you see, we will compare the number of occurrences in each and calculate the difference. Once we calculate the difference, we add it up, and that brings us to a number. We'll see how large or small that number is, and basis that we'll be able to then determine if this data distribution represents a normal distribution or not. All right. So, all right, that's a fairly hairy diagram, but let me try and walk you through this. So, and the color coding also has a meaning, but we'll get to that. So where does all this start? So given a data distribution, if you remember, this was our problem statement. This is the data set, and we are trying to determine if this is a normally distributed data set. So the way this would work is, first and foremost, we would calculate the mean and the standard deviation of the data set. So how do we do that? Well, that's pretty simple. You can use inbuilt formulas for mean and standard deviation within Excel to get that information. What you can also do is you can try and run summary statistics either from any statistical package, or you can also utilize the data analyze option within Excel to generate summary statistics on this. And that is another advantage that we'll look at shortly. Once you've determined the mean and the standard deviation, what would you do with that? The purpose of that is that, remember that given a mean and given a standard deviation, you can always plot the normal data set. If you guys recall from a previous video, and I'll leave a link again to that, remember that you can always describe a normal distribution by just two numbers, by the mean and the standard deviation, right? And that's why this is important, so we'll calculate it. What's next? What's next for us would be to calculate the appropriate bin, width, and derived class intervals. Why is that important? Remember, we just looked at comparing both of the distribution by class interval, so one class interval to another. So if you want to compare it, you'll have to first create that class interval, and then compare the frequency or the occurrences for each class interval. Finally, find actual data set frequencies for each class interval. So once you have the class interval, just plot the frequency for each interval. All right. So that kind of brings us to the end of the first part of the concept. Now, once you have dealt with the actual data set and derived the class interval, the frequencies, the next thing that we need to do is we need to determine that, given the mean and given the standard deviation that we have to determine what would be the class intervals for the normal distribution, and then derive the frequency for that normal distribution. In other words, if if we had to look at a normal distribution for this mean and standard deviation, then what would be the frequency for each class interval? Remember, the class intervals will be the same between the actual observed data set and the theoretical normal distribution of the data set. All right. Finally, let's come to the next section. So on this section, what we'll do is looking at the actual frequency and the theoretical frequency of the distributions. We will calculate something known as the chi-square statistic. Basis the chi-square statistic, we'll then also use the degrees of freedom of the distribution. Once we use the degrees of freedom of the distribution and the chi-square statistic, we will be able to derive the much maligned p-value. And an important thing to bear in mind is that if the p-value is greater than 0.05 in this case, then your data set is normal. So remember that all of this constitutes a part of a hypothesis test. On this current hypothesis test, remember that the H naught or the H null of this hypothesis test is that the data set is normal. Okay, and the H alternate is that the data set is not normal. So if your p-value is greater than 0.05, then you can say that we can infer. Remember that this is statistics. You're not proving anything. The only thing that you can do is you can infer, you can draw conclusions, but you cannot prove. So what we'll be able to prove in this case, or not prove but infer in this case, is that if the p-value is going to be greater than 0.05, then you can say, you can infer that the data set is normal. All right, so that's the concept in general. Let's move on to the next thing, which is the concept of binning. So what exactly is binning? So remember that binning is the binning is the science or the method of deciding the size of the bin or the size of the class interval. In many different texts and different statistical treatment everywhere, you might see that it is often written that the bin size or the class interval size depends on the domain expert or the subject matter expert. They are best placed to decide what should be the ideal bin size or the ideal class interval size for a given data set. And that is true. However, there are also some statistical methods that one can use. One very common method that is often used is, as you can see on the top left-hand side, is the square root rule. So basically, under the square root rule, first step is to find out the count of the bins or the count of the class intervals. How's that done? You just take the square root of the number of data points and you get to the count of the bins. Once you have the bin count, you can also decide or determine the bin width, which is nothing but the range divided by the count of bins. What is range? Remember, range in this case is going to be the maximum value in the data set minus the minimum value in the data set. A more advanced version of this is known as the Rice rule. The Rice rule doesn't take a square root, it takes a cube root. However, we'll stick to the square root in our example. It's going to make things much simpler and easier for us. The next thing that you see is the Sturge's rule. Now, the Sturge's rule uses a logarithmic formulation, as you can see. Sturge's rule, again, it can be used. It is, I would say, more appropriate than the square root rule many times. However, there is a limitation. Remember that the Sturge's rule is better suited to continuous data. When you already know, that the data set is continuous, is close to normal, that's when Sturge's rule is applicable. Which then brings us to two more advanced rules in here. And these are kind of similar, as you'll see by the formulation. So the Friedman-Diaconis rule, again, is a very robust rule. You can use this for most statistical calculations. The Friedman-Diaconis rule relies heavily on the interquartile range, or the IQR. Just to refresh our memories, the IQR is nothing but the difference between the first and the third and the first quartile. The n in the formula is just the number of data points, or the number of observations, the total number of observations of your data set. So if you remember the problem that we are trying to solve, which is if the data set is normal, it has 100 data points on it, so n would be 100 in this case. Scott's rule again is similar in formulation. You will see that it is still proportional, directly proportional to the cube root and the inverse powers of n, which is the number of observations, similar to the Friedman-Diaconis rule. The only difference is we're using a constant 3.49, and this also depends on the estimate of standard deviation. This is based on statistical entropy. This is again a rule which you will not commonly see being used. All right, so this is a bit about binning. Why is this important? Binning has a lot of applications. If you want to draw conclusions using a histogram or a frequency polygon-like apparatus, it is important that you select the right bin size to draw the right conclusions. It has a lot of applications in data science as well. Very often in data science and other disciplines, what you'll find is discretization of data. So what is discretization? If you're trying to convert continuous data into, let's say, a discrete equivalent of that data set, the way that is generally done is that you take blocks of continuous data and convert it. First of all, you convert them into class intervals, and then each class interval can be thought of as discrete data. This is very important, especially when somebody is trying to develop different data models within data science. So as you can see, binning has wide-ranging applications in different statistical treatments. For our example, we will limit ourselves to the square root rule, primarily because it will be the simplest for us to use and demonstrate. Generally speaking, what I would recommend is that you rely more on the Friedman-Diaconis rule for those cases where bin size and class interval size is very important to the topic at hand. All right, so let's move on and extend this further. All right, so this is the original data set that we were trying to check for normality, right? So how do we deal with this? So remember that the first step of this is to calculate the mean and the standard deviation. All right, so how can we do that? That's a fairly simple exercise. If you were to calculate the mean and the standard distribution, the standard deviation, we can fairly easily do that by using known formulas. So the formula to use is average, right? You can just select the data set, calculate the average. There we are. That's the average value right there. And then once you've done that, what we can also do is calculate the standard deviation. So this is the standard deviation formula that you can use, STDEV. Use the simplest variant here, select the data set, and you have the standard deviation as well. Both of these will be used. And then, of course, it is also helpful in this case to calculate the minimum and the maximum of this data set. All right. So for minimum, you can use the minimum formula within Excel. Just select the minimum, select the data range, and you have the minimum. Let's do the same for max. Pretty intuitive. There's a formula called max within Excel. Select the data range and you have the max as well. All right. So these are the 4 key data points that will be very useful for us. In addition, what you could also do is sometimes if you just select this data set and within this, if you have the data analysis pack installed, then you can run summary statistics as well. So if you do this and if you go to data analysis, and within data analysis, let's say if you were to choose the option for descriptive statistics, right? Choose descriptive statistics, click on OK. Then the first thing you will have to do is select the input range. What's our input range? Input range is going to be the range or the data range, right? And then where do we want our output? Let's say we want our output, let's say right here. Okay, so that's where we want our output. You'll have to select at least one of these 4 options. The one we'll select is summary statistics. Click on that, click on OK, and there you are. These are your summary statistics. As you'll notice here, thankfully, we also calculated the same things manually by using formulas. The good part is you can easily corroborate that what you had earlier calculated manually is correct. So you'll see the mean matches right there, 5146.72. Standard deviation 1442.6664. As you know, you can round it off to 6667. And you have the minimum and the maximum values as well. So good. So you can do it by using either method. You can either do it manually, or you can also use descriptive statistics from the data analysis pack option. All right. So that's our kind of first step. What's our next step following this? So our next step following this is going to be creation of the bin size. Remember that we're going to use the square root rule right there. Okay. So step one is let's get the count of bins. All right. So what's going to be the count of bins for us? So remember that the count of bins for us is going to be the square root of the number of data points, right? So let's use square root and the number of data points, right? So just using a count formula for the number of data points, there we are. Okay, and there we are. The count of bins is 10, which is something that we come to expect anyways, because our total number of data points was 100. So the square root of 100 is 10. So that's our count of bins. Now that we have this, let's calculate the bin width. The bin width, or the class interval width that we have here. How do we determine that? So remember that to determine the bin width, what we'll have to do is divide the range by the count of the bins. So what is range? Remember that range is nothing but the max minus the bin. So the maximum value minus the minimum value divided by the count of bins. That should give us the bin width, or the class interval width. Okay, so there we are. So that's our bin width. Our bin width is 737.10. Okay. All right. So why did we calculate this? We calculated this because now the next step for us is to generate the bins, or the different class intervals. So let's begin. So on this one, let's just call it bins. All right. And what's going to be our first bin? So our first bin is going to be the minimum value, and that's our minimum value. It's 2067. Okay. And then what's going to be the next on the bin? So the next on the bin is going to be, remember the bin width is 737.10. So what we'll do is we'll add the bin width to the minimum to get to the next bin value, and the next, and the next, all the way till we reach the max of 9437. Okay, so let's add this here. And once you've added it here, okay, just make sure you do freeze this, otherwise your formula will drag along and you'll not get the right answer. The bin width has been frozen. Now if you drag this, there we are. As you can see, the final value is 9437.10, right? So this is going to be the list that you have for the bins. Okay, so this is our next important step that we have taken here. Now that we have the bins on this, what do we need to do next? The next step that we need to do is we need to be able to compute the number of occurrences for each bin. An easy way of doing that is to use the data analyze pack within Excel. So let's go ahead and use that. Okay, so how do we use that? So the option for using that is, again, remember that within this data, you have the data analysis pack. You go there and scroll. Within that, you will see that there is an option within this for, let's say, the histogram, right? You can click on that histogram option. And once you have clicked on the histogram option, now, first thing you have to select here is the input range. So what's our input range? Our input range is the raw data set. Okay, what's our bin range? Remember, we just generated the bins, right? So this is going to be our bin range right there. And where do we want our output? Well, we want our output, let's say, so let's say we want to put our output starting in D3, all right, in O3, and then we want the chart output. Yeah, so let's go ahead and generate this. Okay, so there we are. So as you can see that we've now generated the frequency or the number of occurrences or observations for each bin. Let's go ahead and select that. Okay, there we are. All right. So if you remember the concept that we were applying, let's go back to the concept once. Remember that we have to determine the actual data set frequencies for each class interval. That's what this step is. We've now determined the class interval, so the bins right here, and then using the data analyze pack option for the histogram, we also have the frequency for each of them, right? As you can see, it adds up to 100, which is what is the expectation, because remember that we have 100 data points, right? Okay. Now, once you have done that, if you just take a look at this right now, what you have on the screen, you will see that by the look of it itself, even without running the test further, this looks well, quite similar to what you would expect for a Gaussian or a bell curve. So in other words, there, just by visually looking at this, it looks like it might just turn out to be normal, but that's just the visual perspective. Okay, so let's remove it for now on this one. Okay, and let's study it further. So now that we have done this, what's our next step? Now remember, your next step is now to determine the class interval CDF for normal distribution for a given mean and standard deviation. Okay. If you recall, in a previous video, we had taken a look at the concept of cumulative distribution function. What is a cumulative distribution function? Remember that a cumulative distribution function gives you the probability density of all the points to the left of a given z-score. And that's what we're going to use here. Remember that if you subtract the CDF of a certain value from the CDF of the prior value, what you will receive is going to be the probability density of that particular class interval or that particular bin. Okay, so let's begin. So what do we have here? We have the bin, we have the frequency as well, right? And remember that this is the actual frequency. This is the actual frequency. Now what we need is the theoretical. What we need is the theoretical numbers. And what do we mean by that? Remember that we are trying to compare the actual distribution that we have here. And remember that what you have in column P is the actual distribution. We're trying to compare the actual distribution with the theoretical normal distribution, right? So in order to do that, the first thing that we need is going to be the different CDF values. Okay, so what is the function for CDF? So if you remember that we can run a norm.dist function, and the norm.dist function can return us either the probability density or the cumulative distribution function, either one of those two. So let's do a norm.dist function. And what are the different parameters for this? So the different parameters for this, for the norm.dist function that we have, is let's use the bin, and then we need to use the mean and the standard deviation, because remember, every normal distribution can be described by just two numbers, the mean and the standard distribution. So what's the mean? The mean that we have on here is 5146, and then the next thing that we need to use here is the standard deviation, right? Once you've done the standard deviation, remember we have two options, true and false. Remember that we are going after the cumulative distribution function, so we're going to use the Boolean value of true. Okay, there we are, and that's your cumulative distribution function right there. Okay, so all right, this is the value. Okay, let's change that number. There we are. Okay, now all that we need to do is we need to drag this all the way till the bottom so that we can get the CDF or the cumulative distribution function values for all of them. Before we do that, let's just make sure that you do freeze the range for the mean and standard deviation, because they will remain the same for this, right? And once we have done that, you drag it what you have is the theoretical normal CDF, right? Okay. So what is it that we have just calculated right now? So what we have kind of calculated right now, if I was to convert this from the normal number to percentages, you'll see the numbers go up all the way from starting at very low from 2, then 5, all the way up to 100%. In other words, as and when you keep moving from the left to the right, you will cover more and more data points till eventually when you hit the extreme end of the normal distribution, you're covering almost 100%. Remember, it shows 100, but if I was to show you up till a large number of decimal places, you will see it's still not 100. Okay, but it's very close to 100. It'll be 99.999 something. Okay, so what is it that we have calculated? What we have calculated is what is the percentage of area that lies to the left of the point. So for instance, let's say for 11, I've got the CDF as 13. What does this mean? What it means is that about 13% of the data distribution lies to the left of 11. For 15, you can see it is 27. So that means 27% of the distribution lies to the left of 15, right? But remember, what are we trying to do? We don't want the total data distribution density to the left. We just want the distribution density for that specific class interval, right? So to get the data distribution for the specific class interval, all that we have to do is we have to subtract the current CDF value from the prior CDF value, and that's going to give us the CDF or the probability distribution for that particular class interval. For the first one, remember that we don't really need to do anything here because this is the first bin, so there is nothing technically to the left of it, right? We don't have to make that change on the first one. So the first one remains the way it is. It remains as is. But from the second bin onwards, and our second bin is the 2803 number. So from this bin onwards, what we need to do is we need to subtract this number right here and this number right here. Okay, so the distribution, the cumulative distribution function of the current bin and the previous bin will give us the corresponding value for this particular class interval, and not going all the way back to the left hand edge, right? And if you drag it, you have the corresponding bin percentages, the bin cumulative distribution for each of those bins, right? And that's what we have right there. Okay, so what is this? So this is the bin CDF. This is the bin CDF that we have just calculated. So now that we have calculated the bin CDF, what we have to now get is the expected frequency, right? So remember, this is the actual frequency that we had just calculated using the data analyze histogram option for binning, right? But what we now need is the expected frequency. So what is it that we mean by the expected? So remember that this is the percentage. So roughly 2% of the data has to be to the left of 1, right? That's what the bin CDF says here. And then roughly 4% of the data has got to be between 2066 and 2803, right? Roughly 8% of the data has to be between 2803 and 3540.20, right? So basically all that we have to do is we have to multiply the total number of data points, which is 100. You could also use a count function, and then multiplied by the bin CDF gives us the expected number of data points for this normal distribution. So in other words, if this was a normal distribution, then this is the number of expected data points that we have, which means to the left of 2066, you just expect 1.64 data points. In between 2066 and 2803, you'd expect 4%. What is that 4% going to look like? That 4% is then going to look like 3.58 data points. How many data points would that normal distribution have between 3540 and 2803? That would be roughly 8% or 8.06 data points. All right, now we can just drag it all the way till the bottom. So what you have in the expected column right now is approximately the number of data points that you expect. If this was a normal distribution, then this is the number of data points that you expect right here. Okay, as you can see, the sum of the expected also comes very close to 100. It's 99.85, right, which is very close to 100 data points. Now what's our next step? Now that we have the actual distribution and the expected, right? So these are the two important things for us: the actual and the expected, right? This is very similar to when we were exploring the concept. So this is the expected, and this is the green one is the actual, and the blue one is the expected. The closer the green one is to the blue one, the more the chances that the green one is also a normal distribution, right? So back here, okay. Now that we have this, what we need to do next is calculate something known as the chi-square statistic, right? Now the chi-square statistic is a formulation that was given by Carl Pearson, and let's just mention it here first. Okay. So in order to get the chi-square statistic, the formula that you have to bear in mind is that the chi-square statistic is going to be nothing but your expected value and the difference of that expected value from the actual value squared. So we have to take a square of that and then divide that by the expected value. All right. So let's go ahead and write that formula. The formula will be, so let's just write the formula first like this. So it's going to be the actual minus the expected squared. So we'll have to square this and then divide it again by the expected value, right? So this is going to be our chi-square statistic, right? So in this case, what is the value going to be? So this is our actual, right? And then what's our expected? Our expected is what we have here, 1.64, correct? Okay. And then we have to square it and divide it by the expected. So how would we do that? So what you can do is you can use the power function, right? And what are we doing with the power function? What we're doing with the power function out here is we're going to again look at the actual observations minus the expected, and we're going to square it. So this will give us the square, and then this entire thing is going to divide by the expected value, which is 1.64. So that is going to be our formulation for this. Okay. And then all that we have to do is drag it all the way till the bottom, and you have all the chi-square formulations. Now, our next step is going to be to look at the total chi-square statistic, which is going to be nothing but the sum of all of these points. So if you were to add up all of these points, then you get the chi-square statistic right here. Okay. Remember that the larger the chi-square statistic, the farther away or the more different is the curve from the normal distribution. Okay. I know it's kind of difficult for you to make that estimation right now because I'm giving you one number, but just to give you an example, let's say you had a different data set altogether and you calculated the chi-square statistic of that, and let's say your answer was instead of 8.8, your answer was 15. So which one of these two data sets is closer to a normal distribution? Well, the answer is 8.88 would then be closer to a normal distribution. So remember, the larger this number, the farther away the distribution from the theoretical curve or the normal curve in this example. Okay. So let's go ahead and move further. So now we have the chi-square statistic as well. Okay. Our next step is going to be to utilize this number, this chi-square statistic right here that we've just computed, and use the degrees of freedom So what is the degrees of freedom going to be here? So the degrees of freedom here is going to be given by a formula which will be the count of bins. Remember, degrees of freedom is connected to knowledge. How much distinct information are we providing this model? So remember that each bin represents information, right? So more the number of bins, the more the information available. So the count of the bins is the first information that we have. Okay, from this we would subtract 1, right? Why do we subtract 1? Remember that if you only had one bin, there isn't much information for you to build a model. It is only when you start with 2 or greater than 2 is when you start having enough information to build a model. That's why you always subtract 1 in order to get to the degrees of freedom. Finally, remember that there are 2 additional pieces of information which we have used in order to build this. What are those 2 pieces of information? Remember that when we were building this model, the important thing that we were using is the concept of the mean and the standard deviation. So without the mean and the standard deviation, we would not have been in a position to go ahead and create the actual distribution basis that we couldn't have probably computed the bins that we have, because remember that we started off with the minimum, with the range, and then we computed all of that. So that's why this is going to be important for us. And once you have it, now all that you need to do is compute the degrees of freedom, right? So let's just say used information or parameters. You can also say parameters used or parameters available, right? So in this case, what would be the degrees of freedom for us? The degree of freedom that we would have in this is 1, the count of the bins. What's the count of the bins that you have? You have 11 bins. See at the bottom right there. So this is going to be 11 minus 1 minus, you already used 2 pieces of information here, which is your mean and standard deviation, right? So that is going to be your degrees of freedom. All right. So that's VR. Okay, and as one final step, what we have to do is we have to use these 2 pieces of information. We have to use the chi-square statistic that you've calculated and the degrees of freedom to determine the final p-value around this. Okay, and the way you can do this is by using a chi-dist function, right? The chi-dist function will allow you to generate that number. Okay, so there are 2 parameters that this function will take. One is the x, which is your chi-square statistic, and the next one is going to be the degrees of freedom that you already have here, right? And if you use both of them, and this is going to be your p-value on this. Okay, and this is the p-value which will take us to the observations around whether this is a normal distribution or not, right? So let's go ahead and quickly do a recap of what we have looked at so far, right? Before we come to the final conclusion around what this p-value would mean for us. Okay, so how did we begin all of this? So the way we began by looking at this information was, first of all, to understand that given the data set or given the data distribution that we currently have, what is the mean and what is the standard deviation of the data set? Remember that you can potentially do that in a couple of different ways. So what are the couple of different ways? So one, you can obviously use the average function and the standard deviation function, right? That's one way. The other way is you can use the data analysis pack and use the option for descriptive statistics. That will also give you the information on it. Okay. Once we have computed the information of mean and standard deviation, and remember to also calculate the minimum value and the maximum value, which is again going to be something that we will utilize on this, right? So calculate the minimum and maximum value, and then your next step from that is going to be to utilize the right binning method. So what was the right binning method? So remember that there are many different methods. For our exercise, we'll limit ourselves to the square root as an example. Friedman-Diaconis is recommended highly as a robust method. That will give you the bin width, the count of bins and the bin width. Once you have the bin width, what did we do next? We created the bins. Okay, and these were the bins starting with the minimum value. We kept on adding the bin width and kept on getting the succession of bins. Once we had that, what did we do next? We used the option within summary statistics to generate the actual number of observations for each of the bin. This is the actual, right? And then what did we do next? We used the CDF cumulative distribution function using normdist to calculate that if this was a normal distribution given the mean and the standard deviation that we already had, then what would be the data distribution or the data density for each of these bin values. Using that, we calculated what was the data distribution for each class interval. We subtracted the previous CDF from the current CDF to get the distribution for that specific class interval. We then multiplied it by the number of data points that we have right here to give us the expected number, as you can see. Okay. Using that, we then came to the question of calculating the chi-square statistic. Remember, the chi-square statistic in this case is going to be nothing, but it is going to be the square of the expected, as you can see, the expected and the actual. Square of the expected and the actual divided by the expected. When you sum it up, you'll get the chi-square statistic for the entire population. The next step is going to be degrees of freedom. The degrees of freedom is going to be nothing but the count of bins. Remember, each bin represents information minus 1 minus the used information. The used information is mean and standard deviation. Remember, some text would also call it calculated parameters, for example. That will bring us to degrees of freedom. Finally, using the chi-dist, or the chi-distribution function, we'll be able to get to the p-value, right? Now, if you recall earlier on in the video, what I had said is this is essentially just a hypothesis test. What is the construct of this hypothesis test? The construct is that your H naught is that your data set is normal. What is your H alternate? Your H alternate is the data set is not normal, right? Now, since your p-value is greater than 0.05, it means that we fail to reject the null. And we'll obviously cover hypothesis testing in detail in another video. But remember that within the confines of the hypothesis test or statistics in general, remember that you can't prove, I wouldn't say anything, but you can't prove most of the things that you run by statistical tests. You can only infer, right? And in this case, since we fail to reject the null, we can infer that the data distribution that we are looking at is a normal distribution. So this kind of brings us to the end of this video, in which we were trying to explore chi-square distribution, the concept of binning, and how does this all come together. So before we sign off from this video, remember a couple of important things. Chi-square distributions obviously do come with certain limitations, primarily used in categorical data. Also, given the way the behind-the-scenes construct works, for chi-square distributions, the number of frequencies generally is expected to be greater than 5 for the class intervals. All right, so that's all that we had for this tutorial. Thanks a lot for watching and for your patience. See you next time.